Hello again, here Mr. Sorrentino here, going over things from your notes here. And now in this video we're going to talk about 1.3, linear functions, slope, and applications. So here we're getting into slope, which is something we use to describe lines and write the equations of lines. So we're moving towards dealing with that. And slope is a concept that, again, students often confuse different parts of it, confuse coordinates. So let's go over some of the definitions of it. Um, First of all, it's given the symbol m. Not exactly sure as to why. I'm sure there's some kind of historical reason for it, but for whatever the case is. Um, One way it's defined as rise over run, which is basically a vertical change over a horizontal change, or a change in y over a change in x. And that change is often represented in different ways. You know, you might see delta y over delta x, but these two are, formulas for the slope. Basically, if I'm given 2 points, x1, y1, and x2, y2, where again, these two things could be interchanged quite easily. It doesn't matter which one you're naming x2, y2, which one you're naming x1, y1. If I carry through the subtraction of the y coordinates on top, because remember the y's are on top, y's rhymes with rise, and I subtract the x's on the bottom in the same order, which means whichever um, y coordinate I took first, in my subtraction on top, from the same ordered pair, I take the x first on the bottom. And that's going to help me calculate my slope. So it's a pretty simple formula. It's just one that a lot of students will often confuse. Now, there's different ways to find slopes. So let's have a look at different ways it could be represented and asked of you, and so you know how to do it. Now, for part A of example 1, you're asked to find the slope. Now, you have a lot of these good dots right here that are given to you pretty outright, so you could easily define or distances between them. And so, I mean, I could look at it and say, well, if I go from, say, for these two consecutive points, here I'm going up 2, and I'm moving right 1, I could say that based off of that, m equals 2 over 1 or 2. But I could have done that with even bigger points and say, okay, well, what if I went from this point here to this point here? So, okay, well, I go up from here to here. That was up 6. Here I'm going right 3. Remember, up and right are positive directions, down and left are negative directions. And so from that, I would have said that m equals, 6 over 3, again, rise over run. But again, that's still 2 as well. So they both agree to each other. So it doesn't matter which points of reference you use, as long as they're on the same line, you're good. Just make sure you simplify your fractions a little bit. If you're given nothing but coordinates, though, yeah, you could graph it and then count them and things like that, and count spaces like I did for the part A. But again, I just have to use the formula for this. So m, and again, it doesn't matter which one I take to be x1, y1, x2, y2. I want to take the two y coordinates and subtract them. So I'm just going to start with the 7 first, minus a negative 5. Since I started with this point's y coordinate first, I'm going to start with its x coordinate first on the bottom. So I'm going to have negative 1 minus 3. 7 minus negative 5 is the same thing as 7 plus 5, so that's 12. Negative 1 minus 3 is a negative 4, and that becomes a negative 3. So the slope for that line is negative 3. And in a very similar fashion, this is using more of a function notation, but what it's telling me essentially in these cases is that, this means that I have a point at 0, 4 is a coordinate. Because remember, this is saying, okay, when x is 0, the function value, or y, because we always assume that y equals f of x, is 4. So when x is 0, y is 4. When x is 3, y is negative 2. And they do have a couple problems out of your textbook that present it this way. And so if I want to figure out the slope for this, again, it doesn't matter which order I take them. I'm going to take the 4 first for the y, minus a negative 2. Since I took the 4 first from this point, I got to take the x coordinate from that point first on the bottom. And so now I'm going to have a positive 6 over a negative 3, which equals a negative 2. So slopes are pretty simple to calculate as long as you know what you're looking for and that you're keeping your variable straight. Now, slopes are a characteristic of linear functions. And so basically, if you can establish that there is a slope, a constant slope, that means that you have a linear function. So when you look to example 2, you're asked to determine whether or not the table shows a linear function. There's different ways to complicate this, but one of the things that they tend to do most of the time in your textbook, and this is like this, is they're pretty nice and they'll say, okay, well, if you look here as you go from x value to x value, each time here, let's get a pen on here, I'm going plus 1, plus 1, plus 1. They don't have to always do that. Now, if the y's, since the x's are going up by 1 each time, as long as the y's are changing the same as I go from y value to y value, that would indicate that I have a constant rise over a run. So when I look at if I look at this side, that's a minus 3, that's a minus 3, that's a minus 3, and that's a minus 3, which that indicates that I do have a constant slope of negative 3 running between these points, so this is a linear function. Well, this very similar instance here, each one of these are going up by 1 as I move from x value to x value. So if I have a constant change between the y values, that would mean the same thing. So here, I'm increasing by 2. Here, I'm increasing by 2. Here, I'm increasing by 3. Here, I'm increasing by 3. So I see two different slopes being presented in this particular plot. And if I would plot these points, I would see that it would look like it's bending if I was like tracing the line through them. So this one is not a linear function. So what you're looking for when you're just trying to establish something's a linear function. Now, if you have a picture in front of you, it's going to be kind of obvious because you could be. If you only have 2 points, it will be a linear function. If you have 3 or more points and they're not all lining up along the same linear path, obviously it's not linear. And certainly, if you're giving ordered pairs like this, you can plot them and determine that. But you can just look to see if there's a measurable slope between the points and it remains constant. If it does, then you're good. Now we get into a particular format for the equation of a line. Now up to this point, most of our graphing has been just, picking some x values, calculating out the y values, plotting. If it's a linear function, it can be put into this format, which we call the slope-intercept form, y equals mx plus b. This is the format that's most often used because it's the one that actually, that your calculator would make the best use of, because this is also in a function notation, because if you replace y with f of x, same thing. Now, the y, the x, the plus, the equals are all part of the structure of this. They would always be present. The plus sign might change depending on what the value of b is. M and b are constants. They're going to be replaced by numbers in each one of these formulas. So the number that's attached to the x is going to tell you the slope. The number being added to the x term is going to be your y-intercept. So when we look at this, graphing this, if I have it in slope-intercept form, it's pretty easy. So let's look at this first example here. When I look at this is in the right format. The only thing that's different is instead of saying f of x, we're just saying that y equals something. But don't let that throw you. Remember, y is the same thing as f of x. y equals 2x plus 1. Same thing. That means that the slope is 2. And it's often better to think of it as a fraction. It's 2 over 1, which means we go up to right 1. Now, that doesn't help me yet because I haven't figured out a point to start at. I had to figure out one point on the line, and then I could use that slope to find the other ones. Well, that's where this one comes in. That means that b equals 1, and this is the y-intercept. Now, y-intercepts means they cross the y-axis. And if they cross the y-axis, they have to have an x-coordinate of 0. So basically, 0, 1 is a coordinate on this graph. So 0, 1 is a point on this line, and then from there I could plot other points. So I could say, okay, well, if I go up to right 1, up to right 1, up to right 1, up to right 1. I could also realize that because of negatives, negative 2 over negative 1 is also equal to 2. So, and that would tell me to go down to right left 1, down to left 1. Since I usually don't use a ruler for this, I like having all the points that I could possibly have, so I could just graph the line like so. So pretty straightforward. In the next example, B, the issue is we don't have this in slope-intercept form. This is what we would call a standard form. Sometimes it's called expanded form. This form of a linear equation is good for solving systems of equations, which is something we're going to get more into all the way in chapter 6. But for graphing purposes, there's ways of graphing this, but one of the ways that we could graph this is simply converting this into slope-intercept. I want to make this slope-intercept. To turn any linear equation into a linear equation in slope-intercept form, there's only two things I would have to do. Solve for y, and simplify. If I take the 3x plus 4y equals 12, and I would subtract 4x from both sides, or 3x from both sides, in order to start getting the y alone, I would then divide both sides by 4. I have to remember, though, that essentially I am dividing this entire quantity by 4, and since it has two terms, both terms need to be divided by that 4. So y is going to be negative 3/4 x plus 3. And now that's in slope-intercept form, which means that when I look at this, the slope is a negative 3/4, which you can count as either a negative 3 over 4 or a 3 over negative 4. Depending on like how much room you have and where you're plotting things, I mean, one might be more beneficial than the other, or you may use both in order to get as many points as possible. Because this one here means down 3, right 4, whereas this one here means up 3, left 4. They move in the same general direction as a result, and then you would see things line up. That slope doesn't mean anything to me until I'm able to figure out a point that this thing passes through. And so I know that the b value is 3, which is telling me the y-intercept. And since, again, the y-intercept has to cross the y-axis, and anything on the y-axis has an x-coordinate of 0, that means that this point is 0, 3. So 0, 3 is a point on this line. The rest of them are done by doing a negative 3/4 slope. So either down 3, right 4, down 3, right 4, or you go up 3, left 4, up 3, and left 4. And there would be my line. So if I have something that's not in slope intercept form, I can certainly convert it to slope intercept form, and that would work wonders for that. Now what we need to do is look at two special types of lines, because anything that's written in slope intercept form, and I can clearly see the y equals mx plus b format, those lines are going to be slanted. But there's two other types of lines we have to keep in mind, and we want to be able to see what those look like and see what their equations look like. So let's see what they look like. Now, one example would be the equation of something like y equals 2, or y equals any number. What this is indicating is that the y coordinate is always 2 despite the value of x. So that means that x doesn't matter to this. X has no bearing on what the y value is. Y will stay 2 no matter what x is. So if x is 1, y is 2. If x is 2, y is 2. If x is 3, y is 2. If x is negative 1.5, y is 2. So no matter what x would be, no matter what x value would take on, the y value would always be 2. So this is a horizontal line. If I pick 2 points on this line to figure out what its slope is, here's 1, 2, here's 3, 2. I'm going to use the slope formula, but I could probably do it just by counting and things like that. But for the sake of argument, I subtract my y's, I'm going to have 2 minus 2. I subtract my x's, I'm going to have, we'll say just 3 minus 1. Which gives me 0 over 2. And 0 divided by anything except 0. But 0 divided by any other number is just 0. So the slope of this line is 0. So when I have an equation that says y equals a number, it's going to be a horizontal line, and the slope of a horizontal line is 0. What about a vertical line? Now, it doesn't take someone to be a genius for this one. If y equals a number is a horizontal line, then it kind of stands to reason that x equals just some number is a vertical one. And the reason why it works that way is because this is saying that the x coordinate is always negative 3. Since y is not appearing in this formula, y doesn't matter. So y could be anything, x will always be negative 3. So, x could be negative 3, y could be 1. Or it could be 3, or it could be negative 4, or it could be negative pi, which would be something like right here. So basically, x equaling negative 3 would be this line right here. And it's vertical. Now, if I just pick some random points on this, say I'm going to have negative 3, negative 2, and negative 3, 1. Those would be points on this line. And I tried to calculate the slope from those. Well, I'm going to have negative 2 minus 1 on top. I'm going to have negative 3 minus negative 3 on the bottom, which gives me a negative 3 over 0. We talked about numbers having zeros in the denominator before. They're not allowed. They don't exist. This is undefined. Basically, this slope has all rise but no run, whereas a horizontal line has no rise but all run. It's an undefined slope. So basically, a vertical line is going to have the equation of x equaling a number, and the slope of a vertical line is defined as being undefined. So that's the difference between the two. Now these two special cases, although b is not a function, part A was, because basically this is like saying, I could say that this is, even in slope intercept form, I could say it's y equals 0x plus 2. So it isn't slope intercept form, it's also in a function form. This is a function. It passes the vertical line test, where obviously x equals negative 3, being a vertical line. Vertical lines don't pass the vertical line test. Sounds kind of weird, but remember, it's a vertical line test for functions. It's not a vertical line test for being a vertical line. Since these are functions we've been dealing with, even it's written in slope intercept form, we could use functions for various reasons and applications. So let's have a look at a couple of them that you were presented to do. Housing prices in a particular neighborhood increased at a rate of $3,500 per year. If you bought a home in 1980 for $65,000, assuming linear growth, what would it be worth today? Let H be the price of the house and let T be the number of years since 1980. So there's a number of things going on here. First of all, they're telling us that, we're going to have H being some function of T, where H is the price of the house, so it's the Y value, and T is being the number of years since 1980. They don't have to be X's and Y's. There's two things that they are telling us. They're telling us it increased at a rate of $3,500 per year. Well, one of the things that we have to appreciate about a slope, it's a rate of change. Now, usually we say it's a rate of change in terms of y in terms of x. It's an increase of y per increase of x. Well, it could be an increase of dollars per year, where, y is the dollars, x is the year. Or in this case, h is the dollars and t is the year. So basically, the rate of change is 3,500. In 1980, well, I'm not going to say t equals that. In 1980, h equaled $65,000. It wants you to let t be the number of years since 1980. So if we're in 1980, the number of years past 1980 means that t equals 0. So when t equals 0, h equals 65,000. So it's basically telling us we have an ordered pair of 0, 65,000 as our ordered pair. This would be basically my y, or in this case my h-intercept. So basically, the formula I'm looking for is 3,500 T. This would be the B value, 65,000. Since it is a linear growth that we're assuming here, it can be represented in slope-intercept form. And so now, since I am recording this in 2019, I'm going to say today is, 2019. Since it's a number of years past 1980, T would be 39 years. So for me to figure out the price of the house today, I want to figure out what H of 39 is, which is going to be 3,500 times 39 plus 65,000. And if I work that out, obviously if you're watching this video, if it's a different year, then this would be off slightly. But that's how you would go by figuring out. You should at least be able to get to this far. The rest of it would depend upon what you interpret T to be based off of whatever year it is you're watching this video. So I hope we don't have to remake this from year to year. So at the 1960 Olympics, Wilma Rudolph ran the 100-meter run in 11 seconds. In 1988, Florence Griffith Joyner, FloJo, set the Olympic record for the 100-meter run at 10.54 seconds. If the decrease in the time continues at this rate, which should the winning time for the 100-meter run be at the 2004 Olympics? And then they say the actual winning time in 2004 was 10.93. How far was the model off? So it's asking you two questions. We want to figure out a model, calculate what it would predict for 2004, and see how close it was. So there's a couple ways to interpret this. One of the ways, as we saw before, is that, it was letting our x value or our t value in that case be the number of years since a certain year and use that as they kind of zeroed it out. That makes the numbers smaller to work with, but I can actually work with the actual years here. Just so you know, the 100-meter run part, the 100 that's in there, doesn't mean anything. I will see students try to put 100 into this thinking that it means something. It really doesn't. That's the event, but we're looking at the date versus the time it's run. And so the points I'm given that I know would be on a linear function, if I was assuming it was, is that I would have the year 1960, 11 for the number of seconds, and then I would have 1988, comma, 10.54. Now I could have adjusted this by doing this, but this makes it a little easier for me having to do more mental math and figure, okay, well, if 1960 was 0, what's 2004 going to be, and whatever the case may be. So I want to use this to come up with an equation where y equals the time the events run in, and x equals the year. You can make your own variations to this, by all means, but this is how I'm going to go about calculating it. So my slope is going to be 11 minus 10.54 over, since I took the 11 first, I'm going to take its x-coordinate first on the bottom, 1960 minus 1988. And it's okay for me to have a decimal as my slope, especially since I have decimals involved with this. So let me do the calculation real quick. And it comes out to be negative 0.01648, well, 29. That's enough decimal places. I'm going to still use all the decimal places that are on my calculator because it does have memory features on it. So when I carry through the calculator, I might report one number, but actually be using another number. So right now I have the formula y equals negative 0.01649 x plus b. I got to figure out what b is. And the way I'm going to figure out what b is I'm going to go back and take one of these initial points. I'm just going to take the first one for the sake of argument. And I'm going to plug in the x and y values and calculate what b has to be as a result. So I'm going to have 11 equals negative 0.01649 times 1960 plus b. So I'm going to have 11 equaling negative 32.2 plus b, which means b is going to equal 43.2. So that means that my model for this is y equals negative 0.01642 plus 43.2. Now I have a formula. Now I can predict what happens in 2004. So in 2004, and the way I set this up is I let x be 2004. If you accounted for 1960 being the first one, and you let that become your x equals 0, please make sure you're consistent with that. So here I'm going to have y equals negative 0.016429 times 2004, and I would get y equals, I would get 10.28 seconds. And so the model, if I was using those 2 points as the winning, it's predicting the winning time, it's actually off by about 0.65. Going into section 1.4 lecture notes, which deals with equations of lines and modeling, which is kind of misleading because we've already looked at one equation for lines, and that was slope-intercept form. This one's going to focus on another format, which you can see here is point-slope form. And we're also going to talk about linear regression to a certain degree. Although a lot of the things that they're asking you to be responsible for is calculator driven. I'm going to demonstrate some things on the calculator, but I'm also going to talk about some things they may ask you to do in a similar manner to come up with the equation of lines to predict things based off of data. So the first thing, focus our attention on the point-slope form of the equation. Like slope-intercept, this does give us, all the information we would need to draw a line, a point that the line passes through, as well as the slope. These three things here will tend to be numbers. Those minus signs are part of the structure, but they may change to plus signs if I should be subtracting a negative. The only difference is that this particular format gives us a point on the line. It's not necessarily, and probably not going to be, a y-intercept. And since there's many different points on the line, you could have several different point-slope form equations for the same line. That's one of the confusing parts about it, is that you could have multiple equations for the same line. Also, along with that, there's some sign usage that sometimes confuses some students. So when you look at example 1 part A, you're asked to draw the equation of that line. It's already in point slope form, so it's already pretty straightforward. The only tricky part is, and I'm going to do a quick rewrite of it, is I have to be able to look at this as it's saying y minus 2 on the left equals 1/4 x minus a negative 1. That minus sign right here is part of the overall structure of the definition. And so if that's missing, I have to be able to account for it in some way and recognize the fact that this value here is what we're calling h, or x1 in this case. Some still use the h. And this is the y1. So basically, the point that that this line passes through, that this particular equation is giving us, is negative 1, 2, and it's telling us that the slope is a positive 1/4. So I'm going to plot a point at negative 1, 2, and I'm going to go up 1, right 4, up 1, right 4. So there is the line for the equation y minus 2 equals 1/4 x plus 1. The next one is also written in point slope form. There was a couple things I could do about it, though. One, I could recognize the fact that I could rewrite this. I could have also just as easily converted this to y equals 2x minus 4, and have it in slope-intercept form. Because what's going on here is the information I'm given, the point, the x-coordinate is 0, the y-coordinate is -4, which happens to be a y-intercept, which is the same thing that the slope-intercept form tells us right here. And that the m is 2, which is the same thing as 2 over 1. So I could plot the point 0, -4, go up to right 1, plot a number of points using that. So there are the lines that these produce. Again, I mean, it's a simple method of dealing with it. And it's a method that some people overlook because they don't like using it because of the sign issue and remembering that, the minuses should be there. And if you have a plus sign, that means you are subtracting a negative, so the coordinate's negative. And some people forget that a lot, so they tend to avoid this one. But a lot of times the information you're given in a problem relates more to this, and point slope form can be easily converted into slope intercept form, and therefore put on a calculator and things like that. So the next thing we're going to look at is discussing parallel versus perpendicular lines. So there's a couple things you need to remember. Parallel lines, which means they never intersect each other, are always going to have the same slope. And it makes sense because if you have a graph and you have one line going this way, well, the other line has to be moving the exact same way if they're never to touch each other. And so, just because they look like they're parallel on a graph, you should confirm that by looking at their slopes and making sure that they are, in fact, the same slope to show that they're parallel. Sometimes I'll have students that'll tell me, a situation like this, just because the two lines don't intersect each other and the amount of space that they have there, they'll tell me that those are parallel because they don't touch each other. Well, I mean, if you kind of look at it, if I would extend these on forever and ever, I would see that they are getting closer and would eventually intersect. I could also just, find points on those lines, come up with their slopes, and see that they are, in fact, different slopes. The other one that you're often asked to do, and we're not measuring angles or anything like that, which is what in geometry we often do to determine parallelness or lack thereof, is perpendicular. Now, perpendicular means they intersect and form 90-degree angles, much like a vertical and horizontal line. The main thing we look at is that the two lines are perpendicular. Now, this and this are saying the same thing. If I multiply the two slopes together and get -1, that means that the slope of the two lines are opposite reciprocals. So, that means that, another way of saying it is that, M1 would equal -1 over M2 is another way sometimes to explore, which means that if I compare the two slopes, I could see that there was a flipping around the fraction bar and a change of sign. The only exception we don't use for this is horizontal versus vertical, particular, and that's because this one has a slope of 0. This one has a slope that's undefined. And that's because if you do an opposite reciprocal of this, that'd be a -1 over 0, which of course is undefined. I mean, so, there you have it. I mean, that's just another way of expressing it. So keep in mind that this is the same, but most of the time we look at opposite reciprocals, we look at this formula to determine if they're in fact parallel or perpendicular in this case. Same slope is parallel, opposite reciprocal slopes are perpendicular. So in example 2, you're asked to determine if the two lines are parallel, perpendicular, or neither. Anytime you're asked that question, you're asked to determine, you're going to need to know what the slopes are. Here, the slope is 2/3. Here, the slope is 3/2. These are both written in point slope form, which means I can figure out what the slope is very easily just by looking at the number in front of the parenthesis on the x side of things. They're not the same, so they're not parallel. They're reciprocals, but they're not opposites. So that being the case, they're neither. So remember, you're looking for both things to happen, opposite and reciprocal, not one or the other. The next example, again, this is a little on the easier side because this is in slope, the first one's in slope-intercept form, and this one's in point slope. I'm just going to say PS. So they're both in forms that we can figure out what the slope is pretty easily. This one has a slope equal to 2. This one has a slope equal to 2. So for C, this requires a little bit more work because they're not in any form where you could tell the slope immediately. These are both in a standard form where the x's and y's are on the same side. I'm just going to convert the slope-intercept form, much as I did in the previous lesson, by simply solving each equation for y. So this one here, I'm going to subtract 4x from both sides, giving me 3y equals negative 4x plus 12. And then I'm going to divide both sides by 3. Making sure I recognize there are parentheses understood to be up here, and since I'm dividing a two-termed expression by 3, that both terms have to get divided by 3, this becomes y equals negative 4/3 x plus 4. And for the other one, I'm going to subtract 3x from both sides, and I get negative 4y equals negative 3x minus 24. I then divide both sides by negative 4. Over here I'd have y. Negative 3 divided by negative 4 is a positive 3/4. X, negative 24 divided by negative 4 is a plus 6. Now I have enough information to answer the question because here I know that the slope is a negative 4/3. Here I know that the slope is a 3/4. These are opposite reciprocals, and therefore they are perpendicular. So once you're able to determine the slope of any given line, or any two lines, you could then compare them to see if they're parallel, which means they have the same slope and they would never intersect. Perpendicular, which means they have opposite reciprocal slopes and they intersect to form 90-degree angles, or neither, which means they would just intersect and form any other angle but 90 degrees. Please don't automatically think that intersection means being perpendicular. Perpendicular is a very specific instance where they intersect each other, and not just any old time they intersect each other. The next thing you're asked to do is to now write the equation of a line that gives a certain description based off of being parallel or perpendicular to another line. So let's have a look at that. So there's two parts to example 3. They want you to write the equation of a line that passes through 10, negative 3, and in part A is parallel to y equals 2/5 x plus 4. Now, anytime you're writing the equation of a line, there's two things that you need. You need the slope, and you need a point the line passes through. If you have those two pieces of information, you can write the equation of the line in any format. So the two pieces of information I'm going to need for my line in this one, I need the slope and I need a point that it passes through. Well, the point it passes through is pretty straightforward because they come out and tell us. It passes through 10, negative 3. Now, if I go back to the line here, this line here is helping me because I'm comparing my line to this one. And I know it's parallel to this line. And since this is the slope of that line, that means that the slope of my line is also 2/5. So my line has a slope of 2/5 and passes through 10, negative 3. So what I can do is say, okay, in point slope form, I can simply just write it based off of this information as y minus -3, that's the y coordinate it passes through, equals 2/5 x minus 10. And I could go a step further to simplify and say y plus 3 equals 2/5 times x minus 10. So that's an acceptable answer because it's not asking us to do it in a very specific format. However, if you wanted to put it into a particular format, say you wanted to put it in slope-intercept form, all I have to do is solve this for y and simplify it. And so I could say, going further with this, y plus 3, distributing the 2/5 up there, I'm going to have 2/5 x minus 4, because 2/5 of 10 is 4. And I would subtract 3 from both sides, so y equals 2/5 x minus 7. So this would also be an acceptable answer, except this is going to be slope-intercept. So either answer is acceptable for this because they're not telling you what format to write it in. This one here just happens to be usually the most used format, so most of the time you look at answers in the book, unless you're told to write it specifically in point slope form, you're probably going to see it in slope-intercept form more times than often. Part B is really almost the same problem, except instead of being parallel to y equals 2/5 x plus 4, it's now supposed to be perpendicular to that point. So again, knowing this one's slope to be 2/5, when I now look at my line, its slope is going to be a -5/2, so that makes it an opposite reciprocal, and it has a point at that 10, -3 again. And again, with these two pieces of information, as long as I have a slope and a point that the line passes through, I have enough to write the equation of the line in any form. So using the information here, I'm going to have that y minus -3 again, equaling -5/2 x minus 10. And with a little simplifying on the left-hand side, minus a negative becomes a plus. This would be the answer in point slope form. Which, this would be a suitable answer for this because it doesn't tell you what form to write it in. However, if it was a multiple choice item and you didn't see anything written in point slope form, then it might be written in slope-intercept, so you would have to go a step further and say, okay, or 2 steps further, I should say, distribute the -5/2, and then I would subtract 2 from both sides to get y equals -5/2 x plus 22. And this would be the slope-intercept. So again, either format is acceptable because of the way the question was asked. So the thing is always to keep in mind is that no matter what information you're given, if you're asked to write the equation of a line, ultimately you need to be able to determine the slope from the information they're giving you and a point that the line passes through. The last example that we have on here basically deals with linear regression, and it takes up several pages in your notes because there's a lot of calculator usage in it. I'm going to talk about how the problem could be if they don't have you use a calculator, but I'm going to focus a lot on the calculator usage. So let's have a look at that problem. Prescription drug sales. The following graph illustrates the retail sales of prescription drugs for certain years. Model the data with a linear function. Estimate the total sales for 2006 and predict the total sales for 2011. Answers may vary depending on the data points used. ultimately, that's one of the things that I don't really like about it. It's hard to check your work if they say the answers may vary depending on what points you used. And I'm going to explain what they mean by that momentarily. Um, However, the information you have here, in 2000, prescription drug sales was in billions of dollars, it's $146 billion. In 2001, it's $164 billion, so forth and so on. And essentially, what I first did is we put into this graph here, this table to represent the same thing. Okay. And oftentimes you'll often will see, I'm leaving the year in as the X value. You could also just say, since it started with 2000, this is 0, therefore this would be 1, 2, 3, 4. It makes the numbers a little less fraction involved, or, the decimals are not quite as severe. But, ultimately you have to make sure that you're being consistent along the way. So if you're letting X be the actual year, when you eventually have to calculate your predictions, you have to also make sure that's the case. If you made an alteration to have, like, the year 2000 be 0, everything else has to be accounted for in the same way, or you're going to have some values that are going to be quite a bit off. Now, the thing is, if you were plotting these points, you would see they're not exactly linear. They don't line up as a straight line. They're pretty close. And I'm going to show that eventually when I do a scatter plot, you'll see what I'm talking about. However, they're not linear, because if I kind of go back to something we had done in the previous chapter. Each one of these are going up by 1. Whereas this one goes up by 18. This one goes up by 19. This one goes up by 20. This one goes up by 18. And so when you're looking at the grand scheme of things, and if you're looking at a graph that's scaled a certain way, these slopes are not going to be vastly different. That's why they look almost linear, but they're not quite linear. This is not a purely linear relationship, because of the fact that there are different slope measurements as I move from point to point. As I move from X to X, them being consistent, my Y's are not moving consistently in the same way. So this is not linear, but it's close. So now what they would ask you to do is, pick 2 of these points and then write the equation of a line. And that's where you would have different answers coming from, because if I say I chose to use these 2 points. Now I've already determined what the slope was. Based off of just me jumping, the slope, if I use those 2 points, 2001, 164, and 2002, 183. I already got the slope to be 19, which is in billions of dollars per year. My equation, I would say now I have to choose one of these points. I'm just going to choose that one. So the equation I would have would look a little different depending on which one I use in point slope. But I would say, okay, y minus 164 equals 19 times x minus 2001. And, simplifying this, and if I add 64 to both sides, or 164 to both sides, and that would be an equation that I could come up with this. The problem is, if I had used 2 other points, I'd have a different slope, which would also contradict and possibly change the b value I would get in this slope-intercept form. So there could be different equations I could come up with, so that's why there could be a deviation of answers. The best way of determining the best line to use is to use the line of best fit. Now, all this calculator stuff that you see over here, I'm not going to go through it. I'm going to show it, I'm going to demonstrate it as I go through it, but it's all written for you so you could retrace it and things of that nature. So I'm going to demonstrate this on my little calculator here. Let me pull it up. The first thing I want to do is I want to get this data into my calculator. Um, this is a statistical regression, so um, so I'm going to use statistics, which kind of, and I always make sure to kind of explain that because this is why I know to hit the stat button. Um, I have edit, which lets me edit a list of data, which is what this is going to be. There's calculations I could do, like one variable statistics. Notice that linreg, which stands for linear regression, is there. There's tests you can do too, but that's more if you take a statistics course. So I'm going to edit my data. The first thing I could do is I can actually plot a scatter plot. And so what I can do with that is I can come over to I'm going to do a statistical plot, which so this is stat plot. So I'm going to hit second and my y equals at this point. And I can see what kind of plot is on and off. It'll let you do up to 3 different plots. I wouldn't really want to do more than that. So I'm going to turn this one on. I'm just going to make sure I have it highlighted. Just hit enter. It's going to be turned. I can turn it on. This is for a scatter plot, so I'm going to leave that. I have different choices. X list and my X and Y lists are L1 and L2 by default, and that's what I actually had them in for. So I don't have to change anything with that. I can come down here to the marks. I can change them to, those blocks, plus signs, a slightly filled in block, a much smaller one. I tend to make them a little on the bigger side, leave them here. In this one here, I can actually change colors if I want to. Not a big deal one way or the other. I could, I have a number of colors I could change it to. None of them in particular, are very important, but I now have this information. And so if I hit enter and or quit out of here, I have it turned on. If I hit the graph, I may not see anything, so I'm going to hit zoom, and I'm going to choose 9 for zoom stat. And I can see here that this is the plot of my data. It adjusted my X and Y axis so I could see all the data here. So you don't see much of an axis here because of the fact that it's pretty high up. If I looked at a window here, it's starting at 19996. And the max is at 2004, so it's the X minimum is not even negative. The same thing with the Y min, it's not negative either. So you could change that if you want to see a better idea what the graph looks like, but for the sake of our purposes, this is my scatter plot. And as you can see, it does line up pretty well. And if I would come here, for instance, and put in my formula I had down here, that 19x minus 37855, and if I graph it, it fits this pretty well. Okay, so I'm not off too much with mine. However, I want to find the actual linear regression equation. So now, going back to, I'm going to quit out of here. Going back to stats again, I could go back to calc for calculate, and I'm going to choose choice number 4. The X list is L1, Y list is L2, no big difference there. I can choose to store the regression equation. You can just leave that alone and eventually just use the regression equation command. Depending on your calculator model, this may not be available here, so you might have to just deal with that at a later time. But I could now say go to variables and choose Y2 to store it there, and I can calculate it. And what it does is 2 things. One, it gives me the equation of the linear regression. So the equation that is for the line of best fit is y equals a, which is 18.9, plus x plus b, which is negative 37654.4. So I'm going to write that as the linear regression equation here. Again, not very much different. I mean, 19, 18.9, not a big difference. You might say, well, 37855 and negative 37654.4, that's much more substantial difference. Not so much when you're dealing with billions to deal with. I mean, 376. What's this like? This is yeah, 37,654 billions of dollars. And this is 37,855 billions of dollars. I mean, comparatively, they're not that far apart from each other. So, but one of the cool things about doing it the way I had, going back to this, is if I go back to y equals now, you're going to see that that regression equation has been stored there. My other option, just to kind of show it, is that I also could have just came here, went to variables, went under statistics, 5, and under equations, the very first one says regression equation, and they would have popped up the same thing anyway. So, didn't need it there. So, but I know now that y2 has, the actual formula in there. So, I could use y1 or y2 depending on the case may be. Actually, I would prefer to use y2. Also, getting back to what was produced when I did that, these R values. This R value is also a strength of the correlation between them. This 0.999846 means that my scatter plot, those points are pretty close to being linear in the grand scheme of things. If the R and R squared are not following up for you, what you need to make sure to do is go to second, hit the 0 for your catalog. You want to get under D's, so on the matrix you see the letter D here. That gets me into my D commands, and I want to go to diagnostics. It might take a little bit of scrolling, depending on your calculator. And you want to make sure the diagnostics are turned on for this to work. And it should make those R's show up if they weren't showing up before. But the closer to 1 or negative 1 this R value is, the higher the correlation is, the closer they are related to each other. The closer to 0 that R value gets, the less of a relationship there is. So that's kind of a measure, and that's also mentioned in your notes as well. So this indicates to me that we have this equation, this linear regression equation. It's a pretty strong correlation with that. So that means that this would be, if the data is thought to be considered to go on in this manner, it should be pretty close in prediction values, for anything I predict beyond this. So with this information now, I can now answer the questions we're actually asked. We're asked to estimate the total sales for 2006 and estimate the total sales for 2011. Just to make this short and again, get to the end of this video, I'm just going to, basically that means you're just going to go to either this function you created or this function here that's from a linear regression. This one, of course, is better. That's the one I'm going to go with. And I'm going to basically plug these in for x's, because remember, my x's were my years. So if I pull up this again, and go to variables, and go to y2, I just put in the year 2006, I get 259. So that means that the total sales, the estimated total sales for 2006 would be $259 billion. I have to make sure I am putting the right variables in. It's dollars, and it's in billions of dollars. And likewise, I can do the same thing, except now put in the 11. And I get 353.5 billion. And that's in billions of dollars again. Granted, I could have also used the first one I came up with, because it's not that far off again. I would notice some difference in these values. There's going to be some difference Because if I choose to do y1 instead, it's 259. So you can see that part's not very far off. And if I do 2011, that one's not very far off. It's off by zero point 0.5 billion. So as you can see, I shouldn't expect to have major differences between if it's close to being linear as it is, a line of best fit that I come up with by picking my own points, or the line of best fit that is made by the calculator by finding the one that fits all the points the best they can. That's how you do it by hand as well as on the calculator. Be sure to read through the comments and such, and make sure you look over those notes, practice this on your own calculator to get the hang of it, so you can do some more problems with it. If you have any questions, please make sure to reach out to me. Until next time, have a good day.